So good day. Today is the 16th, Monday of November, and we're going to first conduct a quick review, an item analysis of the 4.4 assessment, the Module 4 assessment, the first version. Does anybody have any questions or interests to cover before we get started? Okay, you can see here that the class average for the assessment was a 3.78. So basically 3.78 out of 5. So 75. That was a pretty fair average considering the complexity of the material. So what we're going to do is post a quick reconciliation after we finish walking through the item analysis, and then you can go ahead and complete the reconciliation at any point this week. So you'll have all week to finish your reconciliation for this module. Let's make sure we can Kiana is about to join us here. Good afternoon, Kiana. How are you? I can't hear anything. I don't know if you unmuted your microphone or not, but we're going ahead with the item analysis. So you'll notice that 5 of the questions were designated easy questions, and there were 5 that were considered can I calculate or poor questions. So those are likely the questions that everybody answered the same way because everybody got it right. And so the average score for image C multi-answer was 0.6, and then reverse operation, which 2 digital components operate in a manner, that's 0.28. We'll go ahead and take a look at that one because everyone's score should be a little higher on that one, but on the whole, we'll get started on the ones at the bottom. So this particular analysis, this particular item was problematic for many students in the class. It read, the interface view of a digital component shows a smaller triangular shaped inset or indentation along the bottom side of the simple diagram. This means that the digital component includes a sequence capability. So we're talking about the basic diagram of a digital flip-flop. It has a triangular indentation that's in your study guide. We did have some students that answered correctly, but then other students answered other bogus items. A built-in digital amplifier. There is another diagram, but it's not an inset diagram. Inset means it's an indentation. Does everyone know what I mean by that?
No.
Okay, so let's have a quick look at the study guide. So we'll go ahead and open this up real quick. This is something we called out in class. It's this little triangle right here. There's it's like a triangle that dents into the symbol. So whenever you see a basic logic gate with that chunk out of it along the bottom, you're talking about a DFF, and what's unique about a DFF is that it's the first of the sequential logic gate types that we reviewed in class. Does that answer your question about what an inset triangle looks like?
Yes.
Okay. All right, moving right along. VLSI CMOS chips require 5 volts of power to run the thousands of logic gates made possible by semiconductor advances. This is false. One of the things we want to hammer and hammer and hammer is that CMOS is the, TTL is the old school. It requires higher voltage. It requires 5 volts. CMOS silicon chips require lower voltage because they're running thousands of logic gates. So that part of this statement is true, but the part that isn't true is the require 5 volts of power. CMOS chips require lower power, and that's important when you're dealing with miniaturization. So when you go to old school TTL transistors, you're running at higher voltages, and they take up much more space. And then when you miniaturize, you get smaller and smaller, so you can put thousands in a very small space. And you're using semiconductors, right? You're using the silicon. Those are lower voltages. So just remember that whenever you see CMOS, it's old school. Whenever you see, well, no, TTL is old school and requires 5 volts of power. Silicon, anything that's silicon doesn't require 5 volts. It requires, well, 3.3, 2.1, in some cases a volt and a half. I mean, it can be very, very small amounts of voltage. Does that explain the nature of this question and what the false part of the question is about?
Yes.
Okay. Now on your retake, I may say TTL components require 5 volts to power the logic gates. And that would be correct, because that's the old-fashioned. See, older radios and TVs require more electricity. They're not as energy efficient, right? So just remember TTL is old school. TTL is an acronym that may also mean time to live. Just think of TTL meaning old. All right, next one, multiple choice. Image A. Which color of element is used for the physical materials in modern digital components? See image A below as a reference. So here's the periodic table. The choices that you had were gold. That's the semiconductors here. That's the answer that should have been selected.
That one was an easy one, Dr. Kentop.
Yes. We did have a bunch of people select blue, which are metals. And metals are not semiconductors, they're conductors. So I'm going to try to give you an analogy here. True or false? You can wash dishes with a garden hose.
True, in a way.
True, in a way. I'm glad you said that. Now, a dishwasher doesn't handle the water like a garden hose, right? Garden hose, the water just flows through in a big hose. It just flows open. It's a lot of water. That's what conductors do. So it's like, if you want to get work done with water, you don't use a garden hose. You have to put it in a machine that's going to control the pressure, which we would call voltage, and the amount of flow, which we would call current, of electricity. So a chip is a bit like a dishwasher or a washing machine. When you have arms that swivel around and spray in different directions at high pressure, it's cleaning the glasses and plates and silverware in your dishwasher, because you're not just flowing the water, it's like you're controlling the flow of water, right? So I want you to think of semiconductors as an elaborate electrical machine that controls the flow of electrons, much like a dishwasher controls the flow of water, okay? It increases the pressure of the water. That's the voltage. It increases, it directs, it changes the direction of the flow of the water. So there's all these arms and spray nozzles and stuff like that. That's much more efficient at cleaning your china than just using a garden hose. So if you're using metals, you're not controlling anything. It just flows in a big gush. And you can sort of work with that, but not very well. Okay. I hope that helps. But anyway, pink, these are what are called noble gases. They're inert. They don't like to react with anyone. So most people avoided pink and red, but a lot of students selected this. We use the metals to connect the circuits on the board. And in fact, we actually plate PCB motherboards or circuit boards with copper. That's another question we'll get to in just a minute. Any questions about the last item here? Image A.
No question.
Diodes and resistors. All right, so I kept sending emails and messages saying, please read the websites, please watch the videos, this kind of thing. Diode resistor circuits are used to create the physical version of which logic gate? So if you look in your study guide, basically at the beginning, one of the first links that we give you, it's this link. This is where it gives you the background about TTL and so on. There's actually a picture where it talks about the digital versus the resistor and the transistor, right? There we go. So we have a diode resistor circuit that makes the AND gate and the diode transistor circuit that makes the NAND gate. There were two questions, one for each of those, where I asked, so, oh, wait a minute here. So are there any questions about this? The AND logic gate is the diode resistor circuit. Diode resistor circuit is the AND logic gate. That's where we got that. Okay. There was one that was similar, it had to do with the NAND. It was the other type. So one of the videos talked about how we dope or introduce impurities into silicon atoms. It was very clear, very plain video, very short video, talked about phosphorus that makes it negative. The boron makes it positive, the P-type. P for positive, P-type, N for negative, N-type. The answer is phosphorus. Any question about this? You got to watch the videos. Okay, combinational versus sequential. How do combinational logic gates differ from sequential logic gates? Combinational logic gates lack memory to store previous results. So the combinational logic gates can only operate on what their current inputs are, but they can't operate on previous outputs or previous results. The sequential logic gates have memory that can store previous results. There'll be a similar question on your retake.
Excuse me, Doctor Kentop. I had chose one last answer.
The last answer.
Yeah.
Okay, so the output depends upon previous input values. The word that makes that incorrect is the word previous. So current input values, combinational logic gates the output depends on current input values, not the previous input values. Previous input values are lost. There's no memory. Does that help explain how this is not a correct answer?
Yeah.
Okay.
Yeah, because
I have,
I wasn't sure. I wasn't sure if it's the one first one, which is VLAC memory to store previous results.
Right. So in this one, in combinational logic gates, there are no previous results to consider. It's only the current input values that that generate the outputs. Did we have another question? I heard someone else.
yeah, I just wanted you to explain why answer number 3 is wrong as well.
Answer number 3 reads, yes, thank you for that question. And who was that, by the way?
Shay Noah.
Shenoa. Thank you, Shenoa. I appreciate you inquiring. Hang on just a second. I gotta get, okay. So question number 3, the output does not depend solely upon current input values. The word not is what makes it incorrect. For combinational logic gates, the output does depend solely upon current input values. For sequential logic gates, the output does not depend solely upon input values because there are previous values in memory. So this would be a correct statement that would describe sequential logic gates. Because they have memory, they can store previous input values in addition to the current input values. So the output of a sequential logic gate does not depend solely upon current input values. But the question here reads, how do combinational logic gates differ from sequential logic gates? So the focus is the combinational logic gate, right? And that's a false statement because of the word not. Does that help explain?
Yeah, it does.
Okay. So just remember, sequential does not depend solely upon the current input values because there's memory. They can remember previous values. Combinational, they don't have any memory component. There is no memory register which precludes or prevents their ability to store any previous results, right? They lack the memory to store the previous results. Any other questions about this item? Okay. So, which elements for p-type? Similar question, it was in the same video. Which element is used to dope or introduce impurities in silicon atoms so that they tend to be positively charged, or p-type? So if we say, what does the P mean in p-type? I want everybody to remember positively. What's the N in n-type? Negatively, right? Boron is what's used to dope the thing so that it tends to be positively charged. And that affects the way the electrons flow. Electrons are negative and they tend to be attracted to positive and repelled by negative, and so they end up moving. It's like a gate, literally. It's like I'm attracted to this, I'm repelled from that, I'm driven in this direction because I'm attracted and repelled. That's what's going on. So boron is the correct answer. It was in the video. Are there any questions about this item?
Yes. For first answer, I had put the one first one first and for the one negative charge, I put one.
Right. You just had them reversed.
Yeah.
So one of the things that we want to remember is that the P for phosphorus doesn't match P for p-type and positive. Phosphorus is negative because it has an extra electron and boron. So if you have an extra electron, that means you have electrons to spare. And electrons are what make the charge negative. So when you have extra electrons, it's negative. When you have too few electrons, it's positive. So it's like a bank account. If you don't have enough dollars, well, yeah, I got to be careful about that analogy. But basically, remember that if you have more electrons and you can spare electrons, then you have surplus electrons, and it's the electrons that make the negative charge. The positive charges result when you have too few electrons, and those boron atoms basically have a lot of positive charge in the nucleus of the atom, and there's too few electrons, so they don't balance out. So the overall charge of that element is positive. It's in the video. Okay, let's keep moving. And I need you to speak up if there are additional questions, okay? I'm going to try to move as fast as possible. All right, TTL, digital components use FET, field effect transistors. I made a big deal out of MOSFET in class one day. A bipolar NPN or PNP device made with 2 diode circuits. Yeah, no, the false part of that is the TTL piece, I think. It's in the website on TTL. So if you look at it, it basically tells you about what FETs are. And remember MOSFET, CMOS? That's the new style. This says TTL, digital. That's the old school. So whenever you see FET, that's CMOS, that's silicon, that's the new generation. TTL is the old stuff. So the reason this is false is because this should say CMOS digital components use field effect transistors, MOSFET, right? Everybody get that? Any questions?
No questions.
Okay, so just remember, whenever you see the term FET, that's new stuff. TTL is always old, takes more power. Diode transistors. So we had the same reference to the same website about diode transistors. We showed you a picture a couple minutes ago of how diode transistor circuits, not diode resistor, diode transistor circuits are NAND logic gates. It's right there on the website. Any questions about this item?
No questions.
There it is. Diode transistor NAND, right there. Diode resistor and those are older, simpler logic gates. No, let's go this way. Okay, identify this logic. ID this logic statement, it represents the behavior of which digital component memory register. If it has in, that represents the digital the logic for the DFF. So timeout equals the function out t-1, right? In simple terms, the logic for the DFF says in. It's the combination of a mux with a DFF that turns the in to an out. It kind of loops it. So a memory register gives out what went in. Just recycles the output, basically. Any questions about this? And just remember that if you see out and out, that's memory register. If you see out and in, that's DFF. Okay? It's right in your study guide. Okay, PCB, plating material, according to this study guide. So the accent was rather thick. It was an Indian gentleman who was explaining about how they manufacture PCBs. But there's a really interesting point early in the video where he shows the printed circuit board, right? The printed circuit board material is dunked into a vat of copper, and it's coated or plated in copper. And that's where they get the trace, that's where they get the trace wires on that board. So it looks like shiny lines on a board. Let's now let's see. So when you see these lines, they're basically thin layers of copper. Thin layers of copper that conduct the, and without that copper being laid out for a certain pattern, you don't, I mean, that's how the wires are compacted into such a small space. So I didn't want people to get hung up on a lot of the mechanics, but it was really important to understand that in most cases, copper is used and not other metals. The other metals are too expensive or they don't work as well. So that's one reason why the cost of copper is so high, because it's in such high demand. Are there any questions about that item?
No question.
Okay. A physical material used to create so many cycles per second. What is the material and what is the unit of measure used for the cycles per second? Please refer to image B for a related diagram. So cycles per second, I give you a hint right here. What is this an abbreviation for? Hertz.
Hertz.
Yeah, all the other units don't match. It's not A for amps, it's not V for volts, it's not W for watts, it's Hz, hertz, right? Cycles per second, and it's crystal. So they use a crystal material that oscillates or vibrates. When you pass an electric current through it, it produces a wave with a regular cycle. So regular, you can use it as a watch. Have any of you heard of like crystals in really high-end watches? So in high-end watches, used to be Switzerland had real gears and not crystals, but some time ago, watch manufacturers started to pioneer this idea that you would basically have a crystal. Now this is solar powered, so the battery recharges itself, but there's a crystal inside, it vibrates, it keeps time, has to do with the clock. Any questions before we continue? Just remember that peak to peak or trough to trough is considered a wavelength for one cycle, right? So if you're measuring wavelength, you're measuring from peak to peak or from trough to trough. And if that passes, if one of those waves pass in a second, it's 1 hertz. If one wavelength passes a certain point, if the wave is traveling and it passes 1 wave in a second, that's 1 hertz. So megahertz is 1,000,000 waves. Gigahertz is 1,000,000,000 waves, right? So it's pretty serious stuff. But yeah, crystals are doing that for us. Any other questions? Let's see. Let's keep going. Most common semiconductor. So this was in one of the videos. We discussed some of this in class. But one of the videos was very clear. It said the 3 most common semiconductor materials used in electronic devices. Germanium was used a long time ago, in the early 20s and 30s in Germany. They discovered germanium in Germany, and they invented some of the earliest transistors and used germanium for transistors and semiconductors, right? So germanium is used, silicon is used, and gallium arsenide. I did make a mistake earlier in one of my previous versions of the study guides. I combined germanium and arsenic together, and in one of the revisions I changed that and said, oh no, I don't want to. All right, so it's germanium and then it's gallium arsenide. So germanium, bismuth, no. Remember that these are all metals. So anything that's a metal would not be a semiconductor. Let's say that again. If it's a metal, it's not a semiconductor. It's a conductor. It doesn't semiconduct electricity. It lets electricity flow like water through a garden hose. Okay. Those are the only other options that people chose, but yeah, that fundamental part is going to be really important. All right, so I think most of the rest of these are good. It seemed like nearly everybody got these correct. I want to take a look at this one here. So this was a multi-answer, didn't have a very high average score. So let's look at this. It said, which 2 digital components or logic gates operate in a manner where they reverse the action or operation of a similar component or logic gate? So the key there is whatever the one does, the other does the reverse of. Well, and or are not reverses of each other. In terms of their behavior, they're opposites, where and is more restrictive, but you still get true results from and you still get false results from or. Let's repeat that. So NAND and are reverses of each other. Or and nor are reverses of each other. But if you see the answer choices here, we don't see an and with NAND, and we don't see nor with or. Just remember that you get ands and or. So with ands or ors, they're not exact opposites of each other. This one tends to be the most, this one's the most restrictive and this one's the most permissive. And so in terms of like general behavior, they differ, but you still get trues, you still get falses with ors, and you still get trues with ands. The XOR and XNOR are inverses of each other. They are they're virtual reverse action or operation of each other, and the mux and demux, right? So you're selecting which input and you're selecting which output based on the signal. Any questions about this multi-answer question? We actually went over this, and it's in one of the recorded session videos. Okay. Please keep your eyes peeled. We'll put a a reconciliation option out there in Module 4. You'll see it, and you'll have through the end of the week to reconcile any errors that you have. So there you have it for the item analysis. Are there any other questions before we finish item review?
No questions.
Okay. So we are condensing. You should see now system architecture, I/O, and IoT, Internet of Things. So we're folding a couple of topics together. We're going to blitz one last module, and we're going to squeeze in all of the content that we would in 2 modules, but we're not going to make it any bigger. We have tomorrow and then by next Tuesday. So we have today, tomorrow, Wednesday, Friday, Monday next week, and Tuesday next week to cover a huge amount of material. And what we want to do is break this down and make it real simple. So what's going to happen is that we'll start with very basic concepts and then work our way down into more and more sophisticated concepts. So what I'd like to do is talk about the von Neumann model. So if you have digital components, if you have the digital components that you can use to create computers with, one of the pioneers and legends in the industry is John von Neumann. And he gave us a very basic model that still holds true for all digital systems that have any computing function. They all use the same basic components. You need to be able to label this diagram. Let's take a look at it quickly, and then we'll keep going here. So can everyone see the screen?
Yes.
Yep.
Okay. So essentially, if you take digital components, you can think of the John von Neumann model in 3 zones. And it's very important to understand what we mean by zones. This is a zone, this is a zone, and this is a zone. And I want you to remember that the one in the middle has the most rectangles. So I may give you a diagram and ask you to order it, or I may give you a diagram and ask you to label it, where none of the labels are there, right? So the important thing to understand is that you really don't have a computer if you don't have these components. If you lack any one of these components, you do not have a computer. You have something that comes close, but it can't process any data. So you have to have a place to store the data, the digital information, and the instructions, the programming statements that you create as computer scientists, right? So you use a programming language to write statements about what to do with your software, and that basically tells the computer what to do with the digital information, okay? But the memory has to be able to store both the digital information and the instructions that operate on the data, or you can't get anywhere. And that's why it's listed first. So active memory, or RAM, random access memory. Now this is volatile memory. When we say active memory, that's important because you have active and then you have inactive memory. You have volatile memory and non-volatile. Volatile means as long as you have power, you have memory, but when you turn off the power, it's volatile, meaning it doesn't last without power. It evaporates. So it's like rubbing alcohol. The term volatile means it evaporates. Active memory, random access memory, disappears when the power goes off. Doesn't work otherwise. That's what keeps the memory register looping over and over again, those values. If you don't have the circuit with the electrons flowing and looping and flowing and looping, the moment you turn off the electricity, there's no more loop. It dies. That's the first zone. Any questions about the first zone, memory?
No questions.
Okay. Second zone is the process of data, or the CPU. the central processing unit. CPU stands for central processing unit. The central processing unit actually has three essential components. One is that it has some built-in memory, so that when it's moving data and instructions in and out to operate with, it's got its own smaller memory capability. So this is like that, except it's very fast and it's right next to the arithmetic logic unit. The ALU, or arithmetic logic unit, is the digital component that actually performs binary calculations and computations based on the statements, okay? The register is sort of like, all right, so this is like the workbench. So we use the workshop analogy. This whole thing is the workshop. Everybody with me? Hello?
Yes.
Okay.
Yes.
Okay. Input output devices are like the storage bins and shelves along the walls and the outside of the workshop. When you're doing a project, you take things out of the bins. You put things in and take things out of the bins and shelves, and you put them on the workbench so that you have space to work with. And then the workman or workwoman, workperson, the meister, the master, right? The craftsman or craftsperson. Not to get hung up on gender, but the point is that the skilled individual basically takes tools and materials, right? Think of this as tools and materials on the workbench, and then they take them up in their hands, and you have to have this local ability to grasp and control materials and tools. That's what the register provides, right? It's like the hand that holds. So you have a workbench top that holds more materials and more tools, but you can really only hold a couple of things, materials and tools, one or two, in your hands when you're actually working with it. So this is the craftsman, this is the workbench, and these are the shelves and bins in the, yeah. So what's the controller? The controller is what allows you to sequence the steps of the tasks. So this does the computation, this stores results, this tells you what steps come after which, okay? Now the controller and the clock actually require a button cell battery for that crystal on your motherboard to work. We're going to get into that in a second. Any questions about the CPU though?
No questions.
Okay. Just remember you have one large vertical rectangle here with two horizontal smaller rectangles side by side, right? And then this one, large rectangle, three smaller rectangles, horizontal. That's the CPU, this is the memory. And then you have two larger horizontal rectangles, input and output. The thing I want you to recognize also, look at the arrow here. We have an arrow going in both directions into and out of the CPU. And then you have input and output, the arrow only coming in and only going out. Now, this is really specific and very important. The third zone has to do with input and output. And what's often missed is that this arrangement here and the order it's sitting in is really intentional. So when you power on a computer, the hard disk is a combination input and output device. So a hard disk is both an input and an output device. When you power on the system, it's going to, the CPU is going to say, okay, I need data out of this disk, and it's going to load the memory up with information and instructions, right, for the CPU to start processing. So the CPU is in the middle for a reason, because the CPU is actually giving the hard drive commands to read the non-volatile memory, the inactive memory, the stored memory, the persistent memory. Persistent means you turn off the power, it's still there. Non-persistent or non-persistent means, now don't get confused between non-persistent and non-volatile. So persistent means it is non-volatile. Persistent means it remains. Non-volatile means it does not evaporate. Those are equivalent terms. Does everybody hear what I'm saying? Don't let me trick you on an assessment item. Volatile means it evaporates. Volatile memory, active memory evaporates when the power is off. It disappears. Persistent memory is non-volatile memory, meaning it does not evaporate. It persists. It remains after the power is off. When you turn off the computer is inactive. You still have memory. You still have data and instructions that are stored in the hard drive. Does everybody understand what I'm saying here?
Yeah.
Yes.
Yeah, don't let the tricky words get you. Remember, volatile means evaporate. Non-volatile means hard disk. Volatile means memory. Persistent means hard disk. Non-persistent means memory. If I use the word non with persistent, I'm talking about memory. If I use non with the word volatile, I'm talking about hard disk. Okay? Just remember, permanent, non-permanent. Okay. Now, every single computing device or system uses this. The problem is that you have all these different diagrams. And it's important for you to understand that all right, so there's a couple of caveats here. What are caveats? Exceptions, important considerations. Some I/O devices are dedicated for input and others are solely for output. A display, unless it's a touchscreen display, is only output. A keyboard is only input. A mouse is only input. A printer is only output. If it has a scanner built into the printer, it can scan a sheet of paper and input the digital image. So a all-in-one device that's a scanner and a printer is both an input and an output device. But some are just printers. They only put out printed paper. You can't put printed paper in. Everybody get what I'm saying?
Yeah.
Okay. Yeah, don't let me trick you that way. All right, so philosophically, one thing you need to understand is that hard disks are input-output devices. They're two-directional and they deal with permanent. You have to be able to, all right, so what's the second objective or student learning objective of this module? You need to be able to, understanding von Neumann components. If I give you a diagram or a picture of a digital system, you have to be able to identify the basic components for von Neumann, right? So what do I mean? If I give you a picture like this, I need you to be able to tell me, oh, that's von Neumann, because I have memory, all right? I have a CPU, and then I have reading and writing. So I have data memory, which is digital information. I have instruction memory. That's actually the two components. This and this are actually this and this. Does everybody see that? Kind of, sort of.
May you want go over it one more time, please?
Okay. So in this model, you have digital information or data. Could be a picture of you. And then you have software that has instructions on what to do with that picture. Two different types of memory. There's memory for the digital information and there's memory for the instructions or statements, programming statements that operate on the data, right? So you compute the data based on instructions. And so you have two two different classes of memory. When you look at a picture like this, I want you to be able to say, oh, this is data memory, that's digital information. This is instruction memory. Oh, that's the random access memory, that's zone 1, right? And then I want you to be able to go, oh, the CPU, that's zone 2. And then you have this write out, you have, so writing is an input, right? When you're writing something, you're inputting data into memory. And when it's coming out, so you have input and output. So I want you to be able to look at a picture of a system and say, okay, all those pins, that's input output. This is RAM, that's the CPU. So this is a good place to start. I want to show you this and I want you to spend some quality time and then we're going to close. I want you to go to this website and I want you to look at this anatomy of a motherboard, right? And it's basically shows you some of the same stuff, right? You have electrical power. Here's the CPU. What is that? Memory. Those are memory modules. And then these are other peripherals. Input, output. Communication means input, output. A USB connection is an input, output. You're storing or retrieving data on a thumb disk, or you have a USB cable to a printer, right? That's a network card. So you have data you're sending in and out. So the important point is that you have input, output, you have memory, and you have a CPU. This repeats all the time. And okay, I'm not going to throw something like this at you, not at first, but this is where the memory goes. These are the memory modules. And then this is where the CPU is, right? And then all of these are input, output, input, output. So as long as you can understand first where the CPU is and then where the memory goes, everything else, how much else? All the rest. Just identify the CPU, just identify the memory module slots. That's it. If I point to anything else on here, what is it? Input, output. What's this? Well, those are power connectors, but that's input, output for the power. What about this stuff? Oh, well, that's where you plug in your Ethernet and your HDMI cord to your monitor and your keyboard and your mouse, all that. What's this? Oh, well, that's where you put in a graphics card and you do all that other stuff. That's all input, output. There's the button cell. It's a watch cell battery that keeps the clock from losing its memory. We're going to get into that later. Any questions? Oh, what about all this? Input, output. What about that? Input, output. Memory, CPU, everything else, input, output. It's actually pretty simple. So whenever you see DIMM, that's dual inline memory module, DDR3, that's dynamic. You'll see in the study guide. I'm going to post the study guide later today. I want you to start reading it. But I want you to get into these websites. That's the CPU. Those are memory modules. Everything else is input, output. Okay? Any questions before we close?
No questions, Dr. Kentop.
Okay. I'm going to stop recording.